Okay, so welcome back to another video. In today's video, we're going to calculate this integral, the integral from 0 to infinity of e to the power cosine x of sine of x divided by x dx. So as you can clearly see, just from your observation yourself, you can clearly see that this is not easily integrable. But however, there is one method that we are going to use that's actually going to make integrating this actually a lot easier. So why don't we get started? So just one thing I want to note is that obviously we know that this function over here, it's discontinuous at x equals 0. So the method we're actually going to be doing in order to calculate this integral is we're actually going to be doing some contour integration. So what this means is we're actually going to be integrating over paths of the complex plane. So if you haven't figured it by now, we're actually going to convert from real value functions to complex value functions. And it's going to come out nice and smooth. So let's establish first that what we're going to be using later, first, and then we're going to use it in the future soon. So let's establish Euler's identity, or Euler's formula, that's what I meant to say. So it's defined as e to the power I times x is just equal to cosine of x plus I times sine of x. Okay. So how about instead that when we're converting from real value functions to complex value functions, we change all our variables x into the complex number z. Okay. So this means I'm just going to write e to the power I times z, so cosine of z plus I times sine of z. All right. Now let's actually rewrite the numerator a little bit differently. And so how about this? Why don't we actually write this as over here is fine. Why don't we write this as e to the power I times z, okay? So this just equals e to the power of our Euler's formula, cosine z plus I times sine of z, okay? And then you can actually use our rules of exponents, and we can actually multiply this as a product of the e base, so e cosine z, and then multiply by e sine of z. But notice that we also can use Euler's formula to convert this to as the following: e to the power cosine, that's supposed to be z, then multiplied by Euler's formula, which is just cosine of sine of z, and then plus I times sine of z. Okay, nice. So that's all we can do for now. So and this will come in handy later. So now that we're converting from real values to complex value, how about instead we also define f of z to equal the same function, but replace everything in terms of z, well, over here specifically. So we write this, so we have our function e to the power iz divided by z. And so one thing we want to notice is that in complex analysis, even though there's a denominator with z, it's also known as that there's a singularity. In other words, you could think of this as like it's discontinuous at the point x equals 0 in the real value, but this is we're thinking in terms of complex values. So there's a singularity as z equals 0. So in other words, we can also state that f of z is analytic everywhere, so it's differentiable everywhere except at the point z equals 0. But also we can also use so what we can do is we can actually use the following theorem. So this is known as Koshi's integral theorem, and that says let me just write Koshi's integral theorem, and that says that if we have some piecewise smooth set, well, the curve is it's a loop, so it meets back to its terminal point when you're drawing the path, then the following, that the contour integral at your curve C of the function f of z dz is equal to 0. Okay, so that's over some curve. Okay, so now before we do this, let's actually draw our contour. So let's see, let me draw this in black. And because our bounds are from 0 to infinity, so we're only going to be looking at the positives of our x-axis line. And generally we're also just going to be looking at all positive values, so we're just only really, our contour is we're going to focus on the first quadrant of the plane. So give me some time to draw this out. I'll come back to you in just a bit. Okay, so here's our sketch of our contour over here. So notice that when we're doing contour integration, we're integrating over each path. So we have 4 different paths that we got to calculate. Our C1, C2, C3, and C4. So therefore, in other words, we have to write, we have to calculate, so, yeah, right over here is fine. So, oops. So our contour integral of C f of z dz is equal to, so our contour integral from C1 of f of z dz plus contour integral from C2 of f of z dz, and then plus contour integral from C3 f of z dz, then plus our contour integral from C4 f of z dz, and that's equal to 0. Okay, and one thing, and then a couple things I want to establish with our sketch. So when we have that, our r is our bit. Okay, I'll write it this way. How about this? So first, lowercase gamma is defined as this radius of the smaller circular arc, C4. And in other words, that's another way to put it, is that gamma is supposed to approach 0. So gamma approaches 0, and then our capital R is defined as the radius of the larger circular arc, C2. So in other words, R has to approach infinity. Okay, cool. So, and then, yeah, R reaches from IR, so it's just, this, again, this is, we're dealing with a complex plane. So your X value is just the real value, and then the Y is the imaginary value, or I times Y specifically. Okay, and now with that, let's actually calculate our 4 contour integrals. So here, 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 and here. Okay, and we're gonna calculate this one by one. So first, let's actually start by calculating our first contour integral C at the curve C1. So let's see if I got room over here. That's fine. So 1. So we're gonna calculate C1 f of z dz. Okay. Now we're gonna let so C1 is being integrated along the x-axis. So really, we're actually just dealing with like the real value integration. But for now, let's actually do this. So so we're gonna let z equals x. So, and if we're actually doing use substitution in this sense, so then this would have to mean dz is equal to dx. So then we can write the contour integral C1 f of z dz is equal to, so we're taking limits. We're actually, because we have gamma and r, and we established that r is approaching infinity and gamma is approaching 0. So that means we're taking limits here. So the limit as r approaches infinity and then gamma approaches 0 of the integral from lowercase gamma to r of so let's see, we have our f of z is over here, so we're just plugging z in terms of x. So this is just e to the power ix divided by x, and then dz is just dx. Okay, and now we're actually taking limits. So in other words, this can actually be written as 0 then to infinity of the same function. Okay, cool. So that's all we can do for now. So now let's actually calculate our second contour integral along the curve C2. You know what? Let me draw this in red. How about that? Or not draw, write this in red. Number 2 we're calculating is our contour integral of C2 of f of z dz. Okay, so we are calculating from our curve. So the starting point goes from r and then all the way up to I times capital R. But notice that this is an arc, so what we can do is we can actually use polar coordinates to find our bounds. So using our polar form, so how about we're gonna define let z equals capital R multiplied by the polar form e to the power I theta. For theta is let me also just write because using polar coordinates, because it starts at 0 over here, but then over here polar form it goes to pi over 2. So okay, so we'll let z equals capital R to e multiplied by e to the power I theta. So differentiate that, we get that zz is equal to so that means we just use chain rule. Well, not chain rule. Our rules for our derivative rules for exponents. So this means derivative of I theta is just I, then multiply by the same thing, and then multiply by d theta. Okay, cool. So we have that. Now let's actually just substitute everything back in. So that means contour integral for C2 of f of z dz is equal to, so now we have our bounds, so 0 to pi over 2 of, that means f of z is just e to the I times re theta. Okay, so I theta. Okay, and then divided by z, so substitute that, so it's just I theta, and then multiply our differential. Let me fix that for just a sec. And then multiply by our differential R theta. Okay, cool. And we can actually, these capital I theta cancels from top and bottom, and I is imaginary unit, so I can actually just move that outside. But not only that, I can also write e to the I theta. We just established that that's also Euler's formula, so I'll just write that expansion out. So this is just I, then multiply by the integral 0 pi over 2 of e to the power r times, or I times r, and then multiply by cosine theta plus I sine theta, and then d theta. Okay, nice. So now simplify this out, then I'll just multiply the I into and just distribute over here. So this is I equal theta and E. So this is R, then I cosine theta, and then I square is just minus 1, so square theta, or oops, that's just supposed to be it's just supposed to be sine. Yeah, minus sine theta d theta. Okay, Okay, and then how about I switch the real value term to the front and then move the imaginary part to the back? So that actually means I can actually just factor out the negative. So this is I, then 2, then E, negative R, then we have sine theta, then what is it, minus I cosine theta d theta. Okay, and now when we're taking limits, we're I should have also wrote that the limit as r approaches infinity as well, but that's totally fine. Now when we actually take r to approach infinity, like over here, so we get that e to the power negative infinity, it's just going to, this whole exponential here specifically is just going to equal 0. So then basically we get that it's I multiplied by the integral from 0 to pi over 2 of just e to the 0 power d theta, which is just 1, where if you integrate just 1, you'll get theta, and then evaluate your bounds from 0 to pi over 2, and you're just going to get that's just equal to pi over 2 times I. Okay, how about I actually underline our evaluated integrals? Well, so first I'll just underline this for now, and then underline this, so that way we can keep track of our each iterated our contour integrals. Okay. All right. Next, we gotta calculate our integral of C3. Okay. So let's see. Okay. So it's actually pretty similar to just like before from number 1, because we're actually we're evaluating from our point IR all the way down to I gamma. Okay. Okay. So now, how about we let let z equals so it's going down the imaginary line, so we're just gonna let that be IY. So then dz is equal to I times dy. Okay, and then let's just do this. So this means the integral from C3 of f of z dz is simply just equal to okay, so we're taking the same thing, we're taking limits. So r approaches infinity, and then gamma approaches 0. And then this is going along the curve from IR to I gamma, so that means IR is our lower bound, and then I gamma is our upper bound for this contour integration. Okay, so we just substitute z back into here. So e to the I times y, so it's going to be e to the power negative y divided by y, and then multiplied by I dy. Okay, but I can just move the I outside, but not only that, because r is approaching infinity and gamma is approaching 0, you can obviously see that the upper bound's a smaller number and the lower bound's a bigger number, so this means we have to change our order of bounds of integration. That means we'll end up with a negative, and I'll factor out the I, so it's negative I, then with our new bounds it's just IR and then I gamma of e to the e minus y divided by y dy. Okay, and then taking limits, we'll see that we'll just get that it's just negative I, and then the integral from infinity to 0 of e to the negative y divided by y dy. Okay, nice. So now we have our third. All right, and now the last one we need to do is we need to just calculate our force curve right here, C4, and pretty much the same thing is gonna go down as well. So now we just calculate C4 of f of z dz, and then this is from 0 to theta and then pi over 2. As you can see from this graph that it's sharing the same angles just from like the bigger arc, but now we're dealing with a smaller arc. Okay, so now I'm going to let z equals our polar coordinate form, so the radius we're dealing with is just gamma, lowercase gamma, multiplied by e to the power I theta. So that means dz is just equal to, so it's just the same thing, so just multiply, so it's constant is just I, then multiplied by lowercase gamma, multiplied by ei theta, then d theta. Okay, and now I'll just write the rest. So that means c4 f of z dz is equal to okay, so now the curve we're dealing with is from I gamma to gamma, so that means pi over 2 is going to be our lower bound and then 0 is going to be our upper bound. Okay, and then it's e to the power I gamma, then e to the I theta divided by gamma e I theta, and then multiply with the differential I, then gamma e I gamma, or I theta, then d theta. Okay, then we can factor out some stuff. But I'm also going to take the shortcut and say that also because pi over 2 is bigger than 0, but you know, the bounds are different, so we have to change our bounds, so that means we'll end up with a negative, and I can factor out the I, so it's negative I, and then from 0 to pi over 2, and then also just like the same step, I'm just going to replace the ei theta from here with the Euler's formula, so it's e to the power e to the power I theta multiplied by cosine theta plus I sine theta, then d theta. Okay, and now just like before, I'll just distribute the I into our Euler's formula. So then we get negative I, 0 pi over 2, then e to the gamma multiplied by, so it's I cosine theta minus, yeah, I squared, so it's negative, so it's just sine theta, d theta. And then I'll just rearrange the terms here. So this means that we'll have to factor out a negative. So this is negative I, 0 pi over 2, then e to the negative gamma of sine theta, then minus I cosine theta d theta. Okay, and now we're also, again, there's a gamma, so we're also taking limits as gamma approaches 0. So notice that e to the negative 0, well, the whole thing just be 0 over here, but that's actually going to mean that e to the negative 0 is just going to be, you know, e to the 0, which is just 1. So we're just left with negative I to the integral from 0 to pi over 2 of e theta. Okay, and then so that means e is just a constant, so that means we're gonna get integrate this as just e theta, or negative I times e theta, then evaluate bounds from 0 to pi over 2, and then we're going to get that it's just equal to negative pi over 2 times e to the I, or e times I. We just have a couple more steps to go, and then we'll be close to our answer. Okay, so now that we have our 4 calculated integrals, so of each defined as when we're defining from each curve, so now we can actually rewrite the following. So this means the integral from c of the contour integral of f of z dz is equal to, so our first integral is 0 to infinity of e to the eix divided by x dx plus pi over 2I That's supposed to be a minus over here. So minus, yeah. So minus the integral from 0 to infinity of e to the e negative y divided by y dy, then minus pi over 2 e times I. Okay? And of course this is set to equal 0. However, how about we actually subtract our evaluated values? So that means one side has the integrals and then the other side has the evaluated integrals. So this means we have that it's just, and I'm also going to skip a step here. What I'm gonna do now is I'm gonna replace this power e to the ix back with our what we showed earlier, that it's the same thing as evaluated as e cosine z multiplied by cosine sine z plus I sine of sine z. So again, it's just me skipping some steps, but this means 0, infinity, and then this is just replaced with just e cosine. I'll do this one by one. So how about I write it's supposed to be x. Cosine x, then plus I sine x, and then divided by x dx, minus, so this integral over here, 0, infinity, e to the e minus y divided by y dy is equal to, so I subtract, I subtract pi over 2 times I and then add pi over 2 times e to the I. But what that does is I can actually factor out a pi over 2i, so we get that it's just pi over 2 multiply by I, and then it's factored with e minus 1. Okay, cool. And so now let me expand this e cosine plus I sine z with what we have from here. And then, so 0, infinity, it's e cosine x multiplied by cosine of, that's supposed to be cosine of sine of x, then plus I sine of x, x dx, minus 0 to infinity of e to the power negative y divided by y dy, and then it's equal to this, so pi over 2 I e to the minus 1. Okay, so now you may be thinking to yourself, what now? Well, we're actually one more step closer to the final answer. The last thing now we have to do is, so we're given that our original integral we are asked to be evaluated is that it's from 0 to infinity of e cosine x sine of x over x dx. Well, if you take a look closely, and I'm not going to show that step, but let's say that I'm going to distribute e cosine x to the inside of this expression, so we get e cosine x multiplied by cosine sine of x, and then plus I times e cosine x times sine of x over x dx and all that. The last thing we need to do is we're actually going to equate our imaginary parts. So what this means is, so let me rewind just a little bit when I say equate. So when we're doing equating parts, so that means we set the left side of, we set the left side of our real and imaginary parts. We set it equal to the right side of the real and imaginary parts. So therefore, because they share imaginary parts from both sides, but we also have the format that e cosine distributes sine of sine x, which is has a similar format to our original integral, then that means equating these imaginary parts, we're actually going to get that the final answer is equal to just pi over 2 multiplied by e minus 1. So therefore, conclusion, the integral from 0 to infinity of e cosine x and then sine of sine x dx is simply just equal to pi over 2 multiplied by e minus 1. Okay? And therefore that is our final answer in this box. Alright. Now that's what you call contour integration.